I'm going to talk about the left and right side rectangle approximation methods. All right? Suppose you wanted to calculate this integral. If the function f had an antiderivative, and if you knew what it was, then you'd probably be best off using the fundamental theorem of calculus. All right? What if the function f did not have an antiderivative? Or what if it did have an antiderivative, but you did not know what it was? Okay? For those situations, you might be forced to find an approximation to the integral. One way to find an approximation to an integral is to approximate the area of the corresponding region. Let me draw a picture of the region that might correspond to this integral. Okay, so if the blue curve corresponds to the graph of the function f, then the integral corresponds to the area below the blue curve above the x-axis in between the two purple vertical line segments with respect to the x values a and b. Now, suppose you approximated the area of that region with the following rectangles. Okay? Now, if you approximated the area using those rectangles, you would be using the left side rectangle approximation method. Now, the reason it's called that is because those green rectangles intersect the blue curve on their left sides. If the rectangles you selected intersected the blue curve on their right sides, you would be using the right side rectangle approximation method. Okay? Let me show you what a set of rectangles corresponding to the right side rectangle approximation method would look like. So that method would correspond to using the red rectangles that I've drawn. Okay? Notice that the left side rectangle approximation method would underestimate the correct value, and the right side rectangle approximation method would overestimate the correct value. So for different functions, for different integrals, different methods will underestimate the correct value, and different methods will overestimate the correct value. Notice also that not all my rectangles have the same width. Okay, it might be a good idea to have all your rectangles have the same width, but it's not necessary. Now, let me do an example using the right side rectangle approximation method. Suppose we use the right side rectangle approximation method to calculate this integral. Now, we don't need to use the right side rectangle approximation method because for this one we could use the fundamental theorem of calculus. In fact, I'll go ahead and use the fundamental theorem of calculus to find out what the exact value is. 21 1/3. Okay, now let's pretend that we either didn't know about the fundamental theorem of calculus, or for whatever reason we had to approximate it with the right side rectangle approximation. So let me draw a picture that corresponds to our integral. And the graph of x squared is a parabola. So we want to approximate the area underneath the blue curve and above the x-axis with respect to x values from 0 to 4, right? So let's use the following rectangles. All right, so the first rectangle corresponds to x values between 0 and 2. The second rectangle corresponds to x values between 2 and 3. And the third rectangle, the one furthest to the right, corresponds to x values between 3 and 4. All right, so let's sum the areas of the three rectangles. So the leftmost rectangle, the area would be 2 times 2 squared. The width is 2, and the height was found by evaluating x squared with respect to x equal to 2. Okay, the next area, the rectangle has a width of 1, and the height would be 3 squared. We know that because we have to evaluate x squared with respect to x equal to 3. And for the last rectangle, 1 times 4 squared. All right, and so that simplifies to 8 plus 9 plus 16, or 25 plus 8, or so 33. All right, so it overestimated the correct value. Now, I'd like you to try to approximate this integral by using the right side rectangle approximation method, okay? And so that you have a chance of getting the same answer that I have, please use rectangles with widths that correspond to the same x values as my green rectangles. All right, so pause the video and try to do that now, and then I'll tell you the answer and work it out myself. Okay, so using the right side rectangle approximation method, we would use these red rectangles. Notice that the leftmost rectangle has no area. So let's see, the area of the three rectangles, well, 0 plus 1 times 2 squared plus 1 times 3 squared. And so that gives 4 plus 9, or 13. Okay? So that method underestimated the correct value. Okay? Now, let me repeat that I don't want you to take away from this video that one or some other method always underestimates and this other one, or overestimates. Okay? I can show you examples of graphs where either method overestimates or underestimates. Okay? For example, here's a couple of goofy looking graphs that show you what I mean. And we'll close with these. Okay, so suppose you try to approximate the area of this region with, well, first let me draw it. All right, suppose you try to approximate the area of that region using the left side rectangle approximation method. Okay, so, and suppose that you chose the width of your rectangles so that you got a really bad approximation. Like that. Okay, so the reason your approximation would be so bad is because the heights of your rectangles just happen to correspond to these, like for example, the right rectangle corresponded to the valley. It intersected the graph at the blue region with respect to a valley. So weird things like that could make any of the methods overestimate or underestimate the correct value of the integral. So don't assume that one method is always too big or too small or anything like that. Okay? For specific integrals, different methods will work differently.